Right, guys. So obviously in 5.1, we talked about the kind of types of problems that we were going to be looking at, these so-called street routing problems. And then in 5.2, we started to unpack the basics of the tools that we were going to need to start to solve those problems. So we looked at in 5.2 at the basics of what is a graph, the idea of vertices, the idea of edges, and some of the key ideas behind those. To tell you where we're going, obviously in 5.3, what we're going to be talking about is what are called Euler's theorems and Fleury's algorithm. These are going to be the ways that we are actually able to solve some of those problems. And then in 5.4, we'll see how these can be applied to a couple of those examples that we saw earlier on about the postman and about the security guard, and see these theorems and algorithms that we talk about today being used in practice. So, with Euler's theorems, basically what we're going to do is develop the ideas that are going to help us solve and help us determine if a graph has what's called an Euler circuit or an Euler path. Remember from 5.2, an Euler circuit is a circuit which starts at a vertex and ends at that same vertex and also passes through every single edge on the graph. Whereas an Euler path simply passes through every edge but does not start and end at the same spot. So we're going to talk about the ideas behind both of those. We're going to start with the circuit. So this is Euler's circuit theorem. What Euler's circuit theorem says is that if a graph is connected and every vertex is even, then it has an Euler circuit. At least one, but usually it has more. If a graph has any odd vertices, then it does not have an Euler circuit. To give you a simple example, let's take a look at maybe a graph in the shape of a square. You've got your 4 vertices, something like this. Then obviously an Euler circuit is possible because the graph is connected and every vertex is in fact even, because the degree for each of these vertices would be a 2. So then you would know that the graph has an Euler circuit. Pretty easy to find one. Start at any vertex and just work your way around the square. But let's consider that same example with an extra edge. So now with that extra edge, if we look at our degrees, we've got 2, 2, 2, but now this vertex has a degree of 3, this one has a degree of 1. They are not all even, so this graph would not have an Euler circuit. There's no way for us to start and end at the same point, passing through every edge just once. Now, to use the theorem, obviously, first thing we have to do is make sure the graph is connected. If it isn't, then we can stop right there and say that an Euler circuit is impossible. If the graph is connected, then obviously we start looking at the degrees of the vertices, and if we ever come across an odd vertex, then once again, we know that an Euler circuit is not possible. It is out of the question. If it doesn't have any odd vertices, then yes, we know that there is an Euler circuit. How do we find that Euler circuit? Well, we'll talk more about that with Fleury's algorithm in just a little bit. So just to illustrate this point, let's say you were looking at this graph right here. Clearly, this is not going to have an Euler circuit because this graph is disconnected. Remember, in order for it to have an Euler circuit, the graph must be connected, so you can't have multiple components like we do right here. But let's say we connected it. So let's now say that we drew in a couple of edges to connect our graph. Now what we need to do is start going through and checking our vertices. Vertex A has a degree of 2, so we're good there. Vertex B, 1, 2, 3, 4, degree of 5, and we can stop right there. We can clearly see that there's some odd vertices. That means no Euler circuits are possible. So you can pretty quickly tell if there's an Euler circuit that's possible. Let's go ahead and take a look at one more graph. So we've got one more graph. Let's see if this one will work. Obviously, it's connected. Degree of A is 2. Degree of B is 1, 2, 3, 4, 5, 6. Degree of E is 4. Degree of F is 2. Degree of G is 1, 2, 3, 4. Degree of C is 1, 2, 3, 4. And degree of D is 1, 2, 3, 4. Right away, just by doing that, we can say that this graph does in fact have Euler circuits, and then we could go about finding one. Think about how nice that would have been with our bridges of Königsberg example. Just a reminder, our bridges of Königsberg, we talked about the graph would have looked something kind of like this. And had we known Euler's theorem and we were looking for an Euler circuit, we could have right away spotted that this vertex has a degree of 3 and a circuit isn't possible. Now, we were looking for a path actually in that case, so let's talk about paths in just a second. So basically, the idea behind the Euler circuit is that every time you go through a circuit or through a vertex, you use up two different edges, one to go out and one to go back in. That's why we have to know that the vertices are all even. So that's kind of the idea behind the theorem. But let's talk about the path theorem, because that's really where our problem with the bridges of Königsberg example comes into play. So Euler's path theorem is similar but a little bit different. If the graph is connected and has exactly two odd vertices, then it has an Euler path. Again, at least one, usually more. Any such path must start at one of the odd vertices and end at the other one. In fact, if you think about starting at one odd vertex and ending at the other one, let's not talk about the square, but let's talk about the house that we were talking about on day one for this unit. We had our house. Obviously, this graph was connected. If you look at the degrees of each of the vertices, you end up with these as your degrees. And I mentioned to you that in order to make this house and draw it, you had to start at one of the two dots or two vertices at the bottom and then end at the other one. Now we have a theorem that shows that that is true. Euler's path theorem says that you have to start at one of these two bottom vertices in order to make an Euler path work. Now, if a graph has more than two odd vertices, then it cannot have an Euler path. So again, let's go back to our bridges of Königsberg example, where we were trying to find a path through these bridges. We've already decided that a circuit's not possible because they're odd, but what about a path? And if you look at the degree of your vertices, here you've got a degree of 3, which is okay. Remember, you need 2, and they have to be exactly 2. This vertex also has a degree of 3, so again, that's okay. We would just have to start at one and end at the other. But it turns out that this has a degree of 3 as well. That's not good. And this one in the middle has a degree of 5. If a graph has more than 2 odd vertices, it cannot have an Euler path. Right away, looking at the bridges of Königsberg example, we can now say that for sure it did not have an Euler path. So again, here's kind of talking through that, and you can read through these slides if you'd like to. Obviously, here is the drawing for that, where we now are able to answer that problem by showing that there is not a way, there's no possible way to walk around all the bridges without having to recross some. So now, what that kind of leads us to is this question right here. And this is a big question. This will come into play with a lot of stuff that we'll talk about in section 5.4 is exactly how many bridges are we going to have to cross more than once? Can we cross over just one extra bridge? Or are we going to have to go over a couple extra bridges? The answer to that is actually that we're going to have to cross at least 2 of the bridges, but it really kind of depends on how you draw it. One of the routes is right here. So this would be recrossing this bridge twice and crossing this bridge twice. That would be starting at this part in the middle, going up, over, and continuing to follow these arrows. And what you'll find is that this is a possible graph. But that would be really helpful if it was a circuit, because we do start and end at A. So this would be for an Euler circuit, but really we were just interested in an Euler path. And for an Euler path, it's even easier. We only have to cross one bridge twice. It's kind of nice difference between a path and a circuit. Obviously, circuits are a little bit more difficult because you have to start and end at the same spot. Paths are a little bit more open. So going back to kind of an earlier example, this was they call it child's play, but this was the house example where we added in a couple extra lines underneath. This graph is in fact connected. If we were to check all of our vertices, the degrees end up all being even. That tells us that an Euler circuit is possible, and we can really start it anywhere we'd want, and we can draw this without ever using an edge more than once. However, as we found out with this house example, not all the vertices are even. The top 3 are, but these bottom 2 without the extra part are both odd, which means that an Euler path is possible, but we have to start at either C or D. So again, we already kind of knew that and talked about it, but wanted to make mention of that right here. So let's take a look at this graph and let's see what's possible. We're gonna first check a circuit, and then we'll check a path. Obviously, it's connected, so we don't have to worry about that. G has a degree of 2, A 1, 2, 3, 4, 5. So right away, circuit, not going to be possible, but let's check path. Here we've got a degree of 2, 1, 2, 3, 4, 5 for B, 2 for H, so we're still doing okay. 1, 2, 3, 4, 5 for C. That's not good. Remember, you can only have 2 odd vertices for a path. So this one, like it says over here, does not have an Euler path nor an Euler circuit. How about this one? Holy cow. Man, if you were to sit there and try to figure this one out without knowing those 2 theorems, that'd take a lot of time. But knowing those 2 theorems, we're going to be able to get through this one pretty quickly. Again, we'll check circuit first and path second. Obviously connected graphs, so we don't have to worry about that. Degree of D, it looks like, is 4. Degree of E is 4. Degree of F is 2. For G, 1, 2, 3, 4, 5, 6. A is 2. J is 2. H is 2. For I, 1, 2, 3, 4, 5. Okay, so that takes away circuit. Let's still go for path. We've got 1, 2, 3, 4, 5 for K. For L, 1, 2, 3, 4. For P, 1, 2, 3, 4. For O, 2. M, 2. N has 1, 2, 3, 4. C has 4. Or no, C has 2. And then B has 4. So in fact, there are just 2 odd vertices. That means that there is in fact an Euler path for this graph. We'd have to start at either I or at K, but we would be able to make it work. Now, unfortunately, while these theorems are nice, you can't just eyeball it. You can't just look at a graph and see if it has an Euler circuit or path. But using our theorems, we're able to tell without too much trouble, really, if you think about it, that there is the possibility of a path. So here's, again, kind of explaining that, where it does, in fact, tell us that I and K are the places that we need to start. You have to start at one and end at the other, but it is possible to have an Euler path. Okay. Now there is a third theorem that Euler developed that relates the degrees of your vertices to the number of edges, so we're going to talk about that. So in addition to his path theorem and his circuit theorem, here is Euler's sum of degrees theorem, which says that the sum of the degrees of all of the vertices on a graph equals twice the number of edges. Therefore, the sum of the degrees is always going to be an even number. A graph always has an even number of odd vertices as well. So that's the other part, is the number of odd vertices has to be an even number. All right. So obviously useful information. Here's where I'm going to end this first video and resume 5.3 in another video. But did want to mention to you, this is a really great slide if you can copy this somewhere down in your notes. This table basically breaks down how you can use Euler's theorems based on the sum of the degrees. So if there are no odd vertices, obviously we talked about, that means that the graph G has an Euler circuit. If it has just 2 odd vertices, that's okay. We can at least still have an Euler path. If it has more than 2 odd vertices, so 4 or 6 or 8, then we talked about that the graph has neither a circuit nor a path. And if you somehow come up with 1 or 3 or 5, you better go back and double check your counting. It's impossible. That's what his theorem said for the sum of the degrees, is that there has to be an even number of odd vertices. All right, guys, so that is it for this video. Pretty straightforward stuff. Definitely helps us a lot with identifying whether a path or a circuit is possible. In the next video for 5.3, we're going to pick up where we left off right now, and we're going to actually talk about some methods that we can use to find those Euler paths and Euler circuits to make finding them a little bit easier. That being said, until next time, have a good day.